All right. So today, what we're going to do is we're going to begin the last section of our study of probability. It's also one of the most complex, or can be one of the most complex that we do, but we're going to make it a lot easier. It doesn't have to be. So what we're going to do is we're going to describe something called the normal distribution. And you've heard this before. You've heard of the normal curve, usually, or grading on a curve, all kinds of things about statistics using what's called the normal distribution. So we're going to look at what the normal distribution looks like today. We're going to do some definitions of some terms and then look at some symbols that you must know. Okay? Right? Some symbols that you have to know or you can't make this work. And then we'll do a little bit of math, some simple mathematics, but most of the stuff we're going to do again today is just an introduction to this idea. Okay? All right, so let's get started. So, looking at the normal distribution is used when you have continuous data. In other words, the data can be anything, any number, right? And so for like heights, distances, mass, area, can't be used for items that are discrete. In other words, you can't have part of an item. Okay, so like a person, right? Because you can't have part of a person. And where most of the data is clustered around a central value, okay, with a few extremes at either end. So if you look at the general shape there that they give you, notice that the curve is tallest exactly in the center, right? And then it's symmetrical. Remember the symmetrical we talked about? Symmetrical on both sides, and it gently curves. And it looks, in this particular drawing, as if that line, pink line, is touching the black line. But in reality, it never does. No matter how far you go in each direction, there's an infinitely tiny, tiny little space between, okay? Where there's always a little tiny bit of the data. But the distribution is always symmetrical. Parameters are simply defined as the things we need to know about the distribution, and that's what I want to get in your notes first. And we're going to talk about a few of them that you have to know. And the first one is something called the mean. You've seen the mean before. The mean is what we think of as an average, right? How do you get a mean for something? Add them all up and then divide by the number of items you had. Exactly, the amount of things you had. Excellent. And so the mean is a critical part of using the normal distribution. But the mean there are different symbols that we're going to use for the mean. And the most common symbol for mean is that little M with a long tail on it. This is the Greek letter mu. And anytime you see that, you know you're dealing with the mean. And when I write it, I always exaggerate that leg on it. It doesn't really go down that far, but just so that I know that that's what's going on. So that's that little symbol in your book. Or you can also see it as X with a line over it, and that's literally read X bar. X bar is also another way of writing mean. And you're going to find out that one of them is population mean, one of them is sample mean. It's not going to make any difference to what we're doing at this particular junction. If you were taking a full-on stats class, it would make a lot of difference. But for us, not going to make much difference. But either one of those symbols stands for mean. Okay? Then the next piece that we have is something called the standard deviation. And let's do the symbol, and then we'll talk about what it means. You'll see the Greek letter sigma or small letter s for standard deviation. And again, that has to do with population or sample standard deviation. It doesn't make any difference in what we're doing, but if you take a proper stats class at some point, you'll learn those pieces. And the standard deviation is a measure that describes the spread of the information, right? In other words, it takes the information and puts it in standardized blocks. And we could go through and find the standard deviation by hand, which means we find the means and then we find the variance and we take the standard, we take the square root of it and get the actual number, or how to compute the numbers. But for what we're going to be doing in probability, they always give you the standard deviation for these problems, right? If later we need to find the process, we will, but it's not important that you understand how that number is derived. What is important, though, is that you understand that if it's standard, that means it's always the what? The same on a graph for each problem, okay? So if you have a standard deviation that's a certain size in a problem, then it has to be that size in all the way through. So let's look at
what's the point of inflection of the curve?
Each point of inflection is where the line is crossing the curve. So yeah, so I'll show you right here. So for this one, it's right there. It's where the standard deviation happens. So here's the mean. The mean is always where? In the middle. Yeah? And then as you'll notice that you have 1, right? 2, 3. And over here you have -1, -2, -3. Right? So each one of those numbers represents one standard deviation. So there's 1 standard deviation, 2 standard deviations, 3 standard deviations from the mean to the right. And of course, just like any other number line, we know it's to the right because they use positive numbers. This is still 1 standard deviation, 2 standard deviations, 3 standard deviations from the mean. But since we're on the left, we're below the mean, and that's why we use the negatives to indicate that we're below the mean. Okay? But the spaces, this distance between these lines is exactly the same distance. All right? So the spaces between standard deviation, between the lines of standard deviation, are exactly the same difference. But notice that our graph is a curve, right? So if you look like at this shaded area here, 1 standard deviation above the mean is way bigger space than that space, isn't it? So the spaces themselves change depending on how many standard deviations. And the area under the curve represents the probability of an item happening. So if you look at most of the data for standard deviation, let me just erase them all. Most of the data is right here, between -1 and +1 standard deviations. Okay? Then you get a little bit more data between 1 and 2, right? And then, but between 2 and 3, there's just a tiny little tail, a tiny little bit of data, right? Again, because your curve is symmetrical and it's falling downwards. So that means that all of these areas, these shapes here, are not the same. Right? Yes?
For the negatives, should we say, for the northwest, and say 3 standard deviations below the mean, or to the left? Which one's better for us?
It's going to depend on if you're describing it. I don't think it's going to make much difference. Below the mean or to the left of the mean. We'll look and see what terminology they use. Good question, because in the States I would always say below the mean. But here y'all might say to the left. So, but we'll see when we get into working some of the problems, we'll just see the terminology that they use, and then we'll replicate that. Because it's a very good question, because that's exactly what's going to happen on these questions is you're going to have to draw the curve. You're going to have to label the curve with the proper numbers for the standard deviations and the mean. Then you're going to have to shade the area that you're particularly looking at. And then you're going to have to describe what that means. You're going to get a number, and then you're going to have to describe what that means. So you're going to have to use that terminology, the correct terminology, to make it happen. So we'll make sure we make a note of that. All right? Now, this is what a standard normal curve looks like. But as you can imagine, if you have different kinds of data, not everything is always going to look just like that. So you can see that you have some, like this one is very tall and thin. This one is very short, okay? Then everything in between, right? So you can have different shapes. But for the sake of most data, if we say most data is normally distributed, it really fits this shape. And it's amazing, actually, how many things fit this pattern. Almost everything in nature fits this pattern if you get a big enough population, a big enough sample. So, for example, if we measured all the heights of all the women in the world, then it would replicate this curve, where it would break almost exactly in half, and half of them on this side, half of them on that side, and break into standard deviations, just like this. Most natural data does. If you went and measured the heights of all the trees in the world, or all the types of trees, yes, certainly. Okay, so there is lots of data that fits this type of pattern. But the only way you can be sure that it fits this pattern is if it tells you that the data is a normal distribution or normally distributed. Okay? And you'll know, then they'll have to tell you. Yes?
The standard deviation thing, so is that just like each graph will have like its own standard deviation?
Yes, every set of data will have its own standard deviation. So let me just give you a quick example here. Say we're talking about the heights in this room. Okay, say that we said, and I'm just going to use a number. Don't worry about it. Say that we said that the mean height in this room was 5 feet. I know it's not, but who cares? And then we had a standard deviation of 1 foot, which means that the standard amount that each person's height varied from the mean was 1 foot. So that would mean that this is 6 feet, that's 7 feet, this is 8 feet, right? You see what I'm saying? These are made up numbers. Going down, that means 4 feet, 3 feet, 2 feet. But notice that it's a standard amount, right? And that's what's called the standard deviation. It's a standard amount that it deviates from the mean. So it'd probably be more likely be, 5 foot 6 inches, and the standard deviation would be 1 inch, probably, right? To make it more realistic, but it doesn't matter. So in this case, then you would just add 1 inch to go this way. What would you do to go this way? Just subtract an inch for each standard deviation the other way. Okay? And does it make sense that most of you would be about the same height? But then there would be a few people who are much taller, and a few people that are much shorter, right? And that's what the normal curve is showing you. Okay? Yeah.
In the actual testing, will they say, like, if the mean is this and the standard deviation is this,
Draw the curve. We'll look at examples and see about all the different things that you're going to be asked to do. Most of the time, all you're going to be there, you're going to have the curve. They may ask you to label the numbers, put the numbers in, but you'll have the curve. But it really doesn't matter, because if you're going to draw the curve, you just draw a curve and draw a line. The line down the middle is the mean. 3 standard deviations either side. It doesn't matter. So drawing it is nothing. So which is why they usually provide you with a drawing. Your job is going to be able to is to be able to use this normal curve to determine probabilities. Okay? So reading it is going to be your job, your biggest job. Okay? So, how are we on the normal curve? What's the line straight down the middle? Mean, good. And the lines that go out from there are called what? Standard deviations. How many standard deviations above the mean? 3. How many below the mean? 3. And to know that it's below or to the left of the mean, we always put a little minus, just like we would on a number line. Right? Okay, yes?
Is standard deviation like only a thing on symmetrical graphs?
Yes, because it has to maintain the same thing. So it's only going to be, you're only going to see it on the normal curve. Okay? All right. Now, let's talk a little bit about, before we leave this picture of this one, because I don't want to get into any that have data in them yet, but I want to talk about something. The mean is where? In the middle, right? So in other words, the mean cuts the graph in half. Yeah? So I already know that on this side of the graph is half of the data. What would that be in a percentage? So 50% of the data is above the mean, which means automatically then what? 50% is below the mean. And because these standard deviations are always equal, we know we could be able to tell you how much each one of these is as well. And we're going to look at those. They have a standard amount as well. Because what we're doing here to measure probability is we're actually measuring the area, the space under the curve. So it's really an area measurement, just like you're finding area for carpet or area of a room. So, and because they're standard, they have the same values. So, for example, I think this one is 34.1%. So 34.1% of the data falls within that range. Now, it's very unlikely that when you're measuring stuff or you're finding probability that you're going to land right on one of those lines, right? Usually your data is somewhere between. So knowing those values doesn't help you that much, except for these two. So if I tell you it's everything above the mean, then I don't have to do any math. Why? Everything above the mean is what? 50%. If I tell you it's everything below the mean, I don't have to do any math. Why? 50% of the data falls below the mean, right? Okay? Make sense? Yes.
Sorry, I missed the bit about why, like, the standard deviation is, like, what is it, 34?
34.1% is just this area. Don't worry about it. You'll see it. Don't worry about it. Okay? It gives you all the areas on them. Yeah, so it gives you, yeah, you'll see those areas in just a second. All right, yeah, they're rounding them a little bit more than you're using decimals. We'll see it in just a minute. Okay? All right. But it just reinforces the idea that it's a standardized amount. Okay? All right. Well, most of the time, the data is not going to fall neatly on one standard deviation. Okay? So let's say that we had something with the heights. So let's just go to their example here. So here we have, consider the distribution of heights with a mean of 150 centimeters and a standard deviation of 5 centimeters. Okay, so don't worry about that stuff there yet. I just want you to look at the graph right now. So here you see the mean, the number right in the center is 150, right? They said that's our mean. And we have a standard deviation of 5 centimeters. So that means as we go to the right, we're going to add 5 each time. As we go to the left, we're going to subtract 5, right? And this number line here they're calling it their Z-scale, but you'll see it's just using standard deviations. So the graph itself is going to use the actual data. Okay? This number line is giving it to you as just simply a number of standard deviations. So if I ask you, what is one standard deviation above the mean for this particular one, you would say what? 155 centimeters. Okay? Make sure that you get your units when you're answering your questions. All right? Is everybody okay with that? Now, but again, most of the time, your data that you want is going to fall in the middle somewhere. And so if it doesn't fall exactly on a standard deviation, then I'm not going to be able to just use those standard percentages, those standard amounts to find the area under the curve. Instead, I'm going to use what's called a Z-score. Okay? So let's look at how to find a Z-score. All right. The Z-score is simply the data point you have. So let's say we had 120 centimeters. Okay? So your data point minus mu, what's mu stand for? The mean, excellent, divided by the standard deviation. And the mean and the standard deviation, they have to provide for you in order to make this work. And they're also going to have to tell you what score you're looking at, okay, or what number you're looking at, data point you're looking at. So, for example, in a minute we're going to look at one where we want to know what the average weight of a backpack is, and so they'd have to give you a weight to compare. Okay. All right. So you're going to be finding lots of Z-scores. And that's going to be our exercise today. You're just going to practice using that formula. Now, I'm going to tell you that, and then I'm going to tell you some more information that we're not going to use, but you need some background. Because I'm going to show you how these are done on your calculator, and your calculator is what you're going to be using to do these. All right? So, everybody have your calculator with you. If you don't worry about it today. We're not going to use it. So you're going to do Z-scores with your calculator. But next time, make sure you bring your calculator. Okay? Because I'm going to show you the keystrokes you're going to need. And in order for you to make sure that you can do them when you get to the assessment, you need to do them over and over and over again so you know exactly which thing to do. It's very easy. The calculator even gives you a list of things you need to put in, right? So, consider yourself lucky. At university, I made the students do all standard deviations by hand, all the means by hand, and then use the chart to read all of these. I was evil. But here you get lucky. So look, for example, here. We have consider the distribution of heights with the means. So there you go. So that's just an example of the thing we look. Here's another example. The volume of milk in bottles has a mean of 1,005 milliliters with a standard deviation of 2 milliliters. Calculate the Z values for, and then they give you two different values, right? So notice that they've given you the mean, and they've given you the standard deviation, and here is where they're giving you just different values to use. And they're just going to have you calculate the Z-score. And you can see the formula. It's your value, so the 1,008, minus the mean, and then divided by the standard deviation. So that gives you a Z-score of 1.5. Yes?
What does the Z-score actually look?
That I'll tell you in a minute. Yeah, we haven't gotten there yet. Okay? So, here they did the same thing for 1,000. Notice it's exactly the same thing. We got minus 2.5. What does that mean, do you think?
2.5 deviations from the mean.
That it's below the mean. Yeah. Yes?
Were they like 1,008?
They just made up some values. The 1,008 milliliters, they said, so what if you had 1,008 millimeters? They're just making up some values. Okay? So I could just easily do it. So here you go. Got your calculators out, guys? Find me the Z-score for this, using this and this, for 1,000, I don't know, Gary. 12. Go. 1,012 milliliters. Okay. Again. Right? Who's got an answer for me? Sorry? 3.5? Okay. So all we did was take 1,012 minus 1,005 and divide that by 2. Right? And that gives us our z-score. Is that what you got? Remember to hit execute after you subtract. If you don't hit 1,002 minus 1,005, execute, and then divided by 2. Enter the blue button there. If you don't, what you're going to do is you're going to get this. And that's not what you want. Right? You can do brackets too. I just like to hit enter, but you can do brackets. You bet. Okay. Enter. Yeah. Did you get it?
Yeah, no, I got it on purpose. I was so confused by this.
It's all right. You're going to do, I think there are like 20 examples.
Okay.
You're going to know it.
Will I be able to use this one in the case with the probability?
I don't think they're going to care, but we're going to use that one for everything else we do in class. So,
That's fine. No, I just didn't know how to use this.
well, but that's what I'm saying. You're going to use it so much that you will. Okay? And if you use the white one, even though it's new to you, then you'll be able to see exactly the same keystrokes, and it's the one the book uses too. So, okay. Yeah.
How am I supposed to figure out this?
Not sure. Okay, guys, let's get back to it. We're not today going to use these to calculate probabilities. The only homework you're going to have is just doing those z-scores so you can practice them. But I do want to talk about this, about using this, just so we can see a few things. But these are things you know from our basic rules of probability. We've talked about this. So, for example, if an event is impossible, what is its probability?
0.
Good. If it's has an equal chance of happening, that's a 50% chance, or a probability of 0.5, right in the middle, right? If it's certain to happen, that's a probability of what? 1. And all other probabilities have to be between 0 and 1, right? So if you get 1.5 as your probability, then you got a problem, right? Now, you can have a z-score of that. Okay. The normal curve is symmetrical, so each area under half of it must be 0.5, right? Half of it. Okay. And then, by looking at the tables, you can also do some addition and see that each one of the standard deviations, each one of the shaded areas, has a specific amount of, and this is what I was talking about a moment ago, of area. So if you were actually dealing with z-score of 2, you wouldn't have to do any calculation. You could just use this standardized area. Yes?
Is the only time, I'm sorry if you already answered this, but is
That's
the
all
only
right.
time that we're going to have to use standard deviations when we're calculating z-score, or will we ever have to calculate standard deviation?
For this course, no. Because this is not a statistics course. In a regular statistics course, yes, you would have to calculate standard deviation. But you're not going to have to here. You just have to be able to use it. So, yeah. And so you see there, the area of one standard deviation above is 0.34, which is, I use 34.1%. That's just a different one. So anyway, and generally, we find hold on a second. We find the probabilities by using tables. But we're going to find it using the graphing calculator. Yes?
The z-score,
Mm-hmm.
is that, did you ever actually explain what that was?
No, I'm not there yet. Yeah, one more page, and then I'll be there. Okay?
So, would it be a good idea
No. Don't bother. Nope. The one I want you to memorize one. Which one do you think? Yeah. That this is 50, that half of it is 50%. I want you to memorize that one. Because if it says everything above the mean, I don't want you to do any math. Now, I do want you to be able to explain it, though. How would you explain that?
Because the mean is the very middle. So
The mean is the middle?
And is 50.
So
half of the data is often half of
exactly. All right? But that's the only one I want you to memorize. Other than that, you're going to use them. Now, all I'm going to do is I'm going to show you what a z-score does, and then I'm going to tell you you're never going to use one in this class. But where are you going to use it? On the exam, they're going to ask you to calculate a z-score, so you still have to be able to calculate it. But how hard is that? Okay? Now, because on the exam, you can use your calculator to find the probabilities. And this is why I want to show you what you would normally be doing in order to find the probabilities, to calculate. You're not going to have to find to use the z-score to find the probability. But here's what it is. A z-score is a number that you can then use to read the probability from a table. Your calculator can do the same thing, and that's what we'll use in this class. But if you want to use the table, you're more than welcome to. So, got some overachievers in here? You'd like to do lots of extension work?
Yes,
well,
we love extension.
Perfect. Well, then you can you can table yourself from now till death, right? It's fine. So here we go. So looking at this table, this is an example of a standard normal distribution table. You're given the formula for z, you find a z-score, and you use that z-score to find the probability or the area of the curve. Okay? So for example, let's just get a z-score. Who cares? Z equals, what do you want it to be? 1.12? We usually take them to 3 decimal places. Okay? So that means I have 3 digits for my z-score. Do you see it? The 1 I'm going to read across the top. Do you see that these are whole numbers? Okay. The first decimal point I'm reading up and down there.
On this thing, it says the opposite.
Okay.
It says the 0 point goes down the column, and then 5 is across the column. And the 6 is the difference.
Okay, hold on. Well, because of the one they're doing, I'm using one with above 1. Okay. So, we'll just use their example. Look at their example. Hold on. So your homework is just that homework on page 18, and that's finding z-scores. Know how to do that particular formula. But again, you don't have to memorize the formula.